right? So again, the idea with hypothesis testing is saying you have some null hypothesis and you want to figure out, you basically want to figure out some threshold at which you would accept rejecting the null hypothesis incorrectly, right? So we normally set some probability of that being the case. So one application for this is goodness of fit, right? So imagine here we have some prediction in red, and then we have these black crosses, which are, you know, this data that we've collected. And one of the questions we can ask is this data consistent with the simulation that we have, right? So maybe you're doing a data Monte Carlo comparison, and you want to figure out if it's reasonable that this data could have come from the simulation. So to phrase it as a hypothesis test, you'd ask, say, your null hypothesis is that the data did come from the simulation, right? We set an alpha significance of 0.05. That's basically saying that we only want a 5% chance of rejecting the null hypothesis when it's really true in the end. And that's common. It's more common in social sciences than physics, but it's a reasonable place to start. So the way we want to ask this is we need a test statistic that we can figure out how that test statistic is distributed under the null hypothesis, right? So assuming that the data really did come from this distribution, you want to say you throw a lot of fake experiments, basically, right? You sort of take this distribution, you Poisson fluctuate all the bins, you calculate your test statistic, you do that over and over again, and then say, how far do I have to go in the distribution before I've sort of used up 95% of the different trials that I've run? And then you check to see if what you observed is bigger or low, is further out or closer in than that critical value that you've calculated. So if it's further out, you say you reject the null hypothesis. If it's closer in, you say that you accept it. So one of the tricks, of course, with all of these things is figuring out a reasonable test statistic, right? Because a test statistic is just a summary number that is just a function of your data that tells you, gives you some measure of what the data is doing. So in this case, what we can do is, because we know that the bin contents in all of these are relatively large, even though counts you should always think of as Poisson ultimately, we can approximate those as Gaussian. So we can start with a likelihood. So likelihoods are almost always a good choice of a test statistic. So we can take the likelihood of observing the data that we've observed given the predicted means, right? So the idea is that the red line is our means, right? It's what everything was drawn from under the null hypothesis, and we make our likelihood. So a likelihood is basically the probability of each bin. We're assuming each bin is basically independent, so the probability of this data coming from this distribution is just the product of the probability of each bin independently. Now, one of the things we often wind up doing with likelihoods, mostly just because sums are easier to deal with than products, is we wind up taking a natural log of it. We also, in fact, almost always take a -2 times the natural log of likelihoods. And what we find is that when you take that Gaussian likelihood and take the -2 log of it, you get something which is a familiar thing, the chi-squared function, plus some constant. So because we think that these are reasonably Gaussian distributed, we can say this chi-squared function, which is up to a constant the same as the -2 log likelihood of this Gaussian likelihood, is probably a good test statistic. So now the question is, what is the probability of finding a chi-squared value at least as large as what we observe in data under the assumption that our null hypothesis is true, right? And this is often how we wind up phrasing these things, right? So we say, we're going to assume that the data really did come from this distribution. We're going to see we have an observed chi-squared, and And we want to know what fraction of the time, just by random chance, would you get a chi-squared value bigger than that, than what you actually saw in data. Now, you can always do that through fake experiments or pseudo experiments, and we'll talk about that a decent bit in today. But in the case where something has a chi-square function, it has some nice properties, right? So the chi-square distribution, well, let's say this. If you have a variable z, which is equal to x minus mu over sigma, right? And x is drawn from a Gaussian distribution with mean mu and standard deviation sigma, then z is drawn from a Gaussian with mean 0 and sigma 1, right? So if we compute this z is equal to x minus mu over sigma, this is true. So that means that we have a chi-squared which is equal to this squared, right, for each bin. So that's the sum of z squared, which is equal to the sum of zi squared. So the question is, what is the distribution that the sum of unit Gaussian numbers which are unit Gaussian distributed squared is? And that's actually defined to be the chi-squared definition, chi-squared distribution. And the nice thing is that there's a lot of routines that exist to help you do the integrals that you need to do without having to actually do fake experiments. So this distribution is defined in terms of numbers of degrees of freedom, right? So the idea is that the number of individual Gaussian deviates squared is basically defines what the probability distribution is. So every time you have one more term added, that's another degree of freedom, right? So you wind up getting a probability distribution that looks like this, right? So when you have 1 degree of freedom, right, it's sort of very sharply peaked with a chi-squared of 0. But as you go to bigger and bigger chi-squareds, it becomes a much broader distribution with the mean moving further out. Nicely, in root, there's just a nice function called prob, which you can give it the chi-squared that you've observed and the number of degrees of freedom, and it will calculate for you the tail integral of it, right? So it'll say how much probability is beyond that observation in the distribution. And that's exactly the thing that you need to do your hypothesis test. Now, just a quick note of the number of degrees of freedom. In this case, there aren't any free parameters, right? So the number of degrees of freedom is just the number of terms in your chi-squared, which is just equal to the number of bins you have. If you've done a fit of some kind, then there are free parameters. And each time you have a free parameter, roughly speaking, that removes 1 degree of freedom, right? So in some sense, every time you have a fit, you've basically added in some freedom which takes away sort of 1 of your degrees of freedom. That is only roughly true. It is possible to have fractional degrees of freedom, right? So let's say you have a fit that includes like a radius and a theta, right? If your radius is 0, any theta at all has to give you the same answer, right? So if your fit is picking a radius that's non-zero, you wind up getting 2 degrees of freedom because both of these variables have an effect on your answer. But as the radius gets smaller and smaller, theta makes less and less of a difference to your answer. So you go from taking away 2 degrees of freedom when r is large to taking away 1 degree of freedom when it's 0. And as it gets close, there's sort of like a fractional degree of freedom that happens as you get closer. So if you're in a situation like that where there's parameters that may not be fully defined in some regions, you wind up having to do fake experiments or pseudo experiments again. in this case, we don't have to worry about that because there are no actual parameters that we're fitting for. Okay, so going back to our example, if you count the number of bins here, there's 20 bins. There's no fit, so that means the number of degrees of freedom is 20. So we would expect that the chi-squared, that if we took the red histogram and we fluctuated it over and over again and calculated the chi-squared each time we fluctuated it, that the distribution of all of those fake experiments would be this chi-squared with 20 degrees of freedom, right? So what we want to do is we place this as our chi-squared observed. I computed the chi-squared between the black crosses and the red line. And then we have our chi-squared distribution, and we want to know what is the probability in there. And again, we can just plug that into root and do prob the chi-squared of 22.02 and 20 degrees of freedom, and it gives you a p-value of 0.34. That's saying that 34% of all of these fake experiments are in the tail. That's much bigger than 5%. That means we can't reject the null hypothesis, right? So as far as our test is concerned, we fail to reject the null hypothesis, so we say that that data is in fact consistent with the prediction that we had. Okay, you could make it doesn't with a p-value as large as we have here. It's not going to be the case, but if it were smaller, there are different levels of significance that you could choose, which if you wanted to be extremely sure that this came from the null hypothesis, you could make that more stringent if you wanted to. I will also say, though, if your bin counts are small, then the test statistic may not be chi-squared distributed, right? So the idea that these bins are Gaussian distributed is only an approximation. And the approximation gets better and better as n gets bigger. There is no hard and fast rule for when it stops being a good enough approximation. People often will say, like a rule of thumb of like 30 counts per bin, but that's not, there are distortions there already that can be visible. So if you have any doubt about whether or not this is a good enough, whether or not the chi-squared distribution is really going to model this probability distribution, then you should probably just go and use Monte Carlo methods, right? Which means that you just go through and you Poisson vary each bin to make a fake experiment or a pseudo experiment, and then calculate the chi-squared of each one of those individually. And that's just an empirical construction of the PDF that you want. So you often will wind up having to do that. Okay. Now, just a quick note about error bars. So we always place error bars. So when I showed the data that I had there, right, the black crosses basically are telling you the error bars. And by convention, we place error bars that have a size of root n. Now, historically, part of the reason why that is in absence of any other information, if you're just given in a bin with n observed, right, then n observed is the best estimator we have for what n true is, n expected, right? But it's not the same thing as n expected. So the error on a bin should be root n expected, but of course we don't know what that is. So we use root n observed. Like I said, since the counts are Poisson distributed, we draw these error bars equal to root n. The idea here is that the expectation, if we ran the experiment many, many times, then the data would fall within those error bars 68.3% of the time, right? So that's like 1 sigma worth. But strictly speaking, data doesn't have any error, right? We place it on the data points by convention, but every error we have, strictly speaking, is on your prediction, not on the data. The data is just whatever you collected, and then you have some models to model what you should have seen, right? So like the data is just numbers that you collect. They don't, strictly speaking, have error on them. but this is the convention, so you'd probably do it. But you should be aware that what's going on there. The other thing is that roughly 2/3 of the bins should be touching the prediction, right? The error bars, if you look at where, do the error bars touch your prediction that you have? If your error bars are reasonably well estimated and your points really did come from the distribution in question, then you would expect about 1/3 of your data points not to be touching the prediction, right? This is just saying that 68.3% of the time, the true value should be within the error bars. So that means that 1/3 of the time, they shouldn't be. So if you ever see a plot where you have every single error bar, the prediction goes through all the error bars perfectly, that is actually suspicious. The p-value you would get would be fantastic, right? But if you see the prediction going through every single error bar, that's very suggestive that someone has overestimated their uncertainties, right? Which is, some people will say, well, we're being conservative, but it turns out that overestimating your errors are just as bad as underestimating in a lot of ways, right? It's not a good thing just to inflate your error bars to hide, mismodeling or something like that. The other thing is that this chi-squared test checks each bin independently in some ways, right? So it's possible that if you were looking at a situation, you could have something where your prediction was like this, and your data was sort of consistently high, like that. If it's consistently high by just a little bit, the p-value might actually be perfectly acceptable. But by looking at that, you can tell that something systematic is happening, right? There's probably a normalization error that you're not accounting for. Similarly, if you have something like this, and you're sort of see it consistently high and then consistently low, that is something like you would think of like a calibration problem where you're consistently misestimating the energy, right? So everything is shifted slightly over. So it's like the distribution is right, but you put it in the wrong place ever so slightly. And then sort of the last one is a case like this where you're sort of overestimated, underestimated, and then overestimated. And that's like a resolution problem where your Monte Carlo does not have the right resolution, doesn't have the same resolution as your data, right? So in all these cases, the chi-squared test might be perfectly fine, but like you should look at the data at some point and see if there are sort of consistent sort of discrepancies, then that suggests that something systematic is happening, not something statistical. And that's something you should always be aware of. Okay, now, these tail probabilities that we've been calculating to determine the significance in our tests are known as p-values, right? And they're sort of the bread and butter of the frequentist way of doing hypothesis tests. So the statement that you should remember whenever you're trying to remember how to do one of these is say, what's the probability of obtaining at least as discrepant a result as I saw in data if we observe, if the null hypothesis is true, right? So whatever our statistic is that we're using, we have some value measured in data, and we want to say, how often should that happen if nothing weird is happening at all, right? Just by complete chance, right? And that's the guiding sort of principle in all of this. There are many asymptotic results that statisticians have come up with telling you what p-values should be, but in real life, you almost always find yourself doing a Monte Carlo study to do it instead, right? So many of these asymptotic results are only true in the limit of infinite statistics, and you don't necessarily get to that asymptotic result particularly fast, right? So very often you have to do a Monte Carlo study no matter what, right? Just a toy Monte Carlo to figure out what your answer is. In root, you can use the T-random3 class to draw high quality random numbers to produce your pseudo experiment ensemble. The other thing to know is that p-values, like if you ran your experiment many times and then redid this and got your p-values, your p-value should be uniformly distributed if your null hypothesis is true. So you actually have an equal chance of getting any particular value between 0 and 1 when you do this. Okay, now the other type of question that you often ask is, let's say I see some sort of excess in data, right? Let's say I say a bump in a distribution. I want to know if the peak I see, some bump, is significant. The null hypothesis is saying that the data is drawn purely from the background distribution, right? And we want to say, can we reject that? So we have to, again, ask, what's the probability that our test statistic is at least as large as what we observe in data? So in this case, we see this, we might think maybe there's some sort of background like this, and you can imagine maybe there being a peak over here, or maybe there being a peak over there, right? Just by looking at it. And the question is, if I did some sort of fit, how often would the fit pick something like this out if the background were just like a flat background, like what you were expecting? So you can do this a number of ways, right? So oftentimes people do like a cut and count. If you have a region where you want to test to see if there's a peak, you sort of like limit yourself to that region, and your test statistic is just the number of events you saw, right? And you take your background, your expected background, you fluctuate the background according to any systematic uncertainties that you expect, and that gives you your fluctuated, systematically fluctuated predictions, and then you Poisson fluctuate that to get the number that you actually sort of think you would see in one of these hypothetical experiments. Then you do that a bunch of times, right? And you see if that number you see what the probability of obtaining that number is, and then compare that to what you saw in data. You could also have a fit if you have an idea of what the shape of the peak should be. You can fit for a peak right in there, and then your test statistic is just your chi-squared or a likelihood value. And so if you do the process you did the data to every one of your fake experiments, you can empirically determine the distribution of your test statistic under the null hypothesis. And then if you have a p-value that's smaller than the limit you set, then you say you can reject the background only hypothesis, and there is in fact, you think there is a peak there. So whenever you're making a claim of significance, oftentimes you'll hear people talk about how many sigma a particular significance is. This is sort of just a conventional way that we talk about this in high-energy physics. So what we actually compute is a p-value. Like I mentioned, the p-value is the area under the curve past the point where we observed in data. So this is the distribution of the test statistic under the null hypothesis, right? The p-value, if you instead think about this in terms of a unit Gaussian, right? So down here, this is a unit Gaussian, and you say, what value along the x-axis would I have to place my bar such that the tail integral of this unit Gaussian is the same as the tail integral of the empirical PDF that I've been sampling from, right? And then that value along the x-axis is our z-score. So since it's a unit Gaussian, z-scores are how many sigma you are away from 0, right? So if your x-axis value is 1, that's 1 sigma for a unit Gaussian. We can easily convert between p-values and z-scores. What I'm doing here is called a one-sided test. So anytime you have something where you're looking for a peak, you're looking for an excess specifically above your background. And so our tail integral is only on one side. We don't care if you were below a certain value, it wouldn't indicate anything, right? So in that case, our p-value is 1/2 times 1 minus the error function of the z-score over √2. And you can get the z-score from the p-value by just doing norm quantile of 1 minus the p-value. Okay, so root contains both of those functions, error function and norm quantile. So normally in HEP, so like I said, in like the social science and everything, 5% as your significance as alpha is really common. In high energy physics, we almost always use something much more stringent than that. We usually call like greater than 3 sigma something like a hint or evidence of something, and then we don't call it discovery until 5 sigma. It's somewhat arbitrary. Those are really, really small p-values in both cases. But a lot of this comes down to the fact that people noticed that many lower significance results went away more often than maybe they thought it would happen. And part of that is because of the look elsewhere effect, right? So if you, the way that hypothesis works in a frequentist sense is that I say, what is the probability by chance that my result is, the probability of my result being more discrepant than this by just chance is less than 5%, right? That means that if you do 20 individual experiments, you've basically guaranteed for one of them to do that, right? Because, like I said, p-values are flat, so if you do this a bunch of times, you're sampling over uniform distribution, eventually you're going to get unlucky and get a very small p-value, and then you think, I can reject the null hypothesis, right? So this is basically multiple testing, right? Anytime you have a case where you're doing multiple testing, the p-value, if you calculate it in isolation, is not really a good reflection of reality, right? So this is a little bit tricky. So if you have a region that you're looking at because you expect something to be there, right? Like you're looking for a particle with a particular mass, that's not really a look elsewhere because you're looking for like a well-motivated thing. But if you say, I'm just going to scan this distribution and look for a peak anywhere, you effectively are multiple testing everywhere, right? So the details of this are complicated. So this came up a lot during the Higgs hunting. In some sense, like there is a look elsewhere effect when one experiment was looking for the Higgs when we didn't know where it was, right? But if one experiment had a place where they thought it was, and then another experiment just went and tested that same region, the second experiment doesn't have a look elsewhere effect because it was just testing the result that the first one saw. It's all winds up being very complicated and people argue about precisely how much look elsewhere effect there is. But roughly speaking, you need to divide your, you need to basically, I guess actually multiply by the number of independent measurements, right? So you're less likely to, has to be twice as discrepant to reject it if you've tested twice, right? Because of the multiple tests you've done. Now I will say, if instead of doing a counting experiment where you sort of cut and count in an isolated region, and then you cut and count in a different region, and you're sort of explicitly a multiple testing that way, if instead you had a fit where you let the position float, the look elsewhere effect is actually taken into account already by the fit. Because the fit, every time you do a fake experiment, pseudo experiment, you have a fit where you let the peak float in it, your p-value actually takes into account. Because there's actually many more ways to find a spurious peak in that. So your probability distribution is much, much broader anyway, right? So if you properly construct your search, the look elsewhere effect can actually already be baked in without you having to do anything particularly special. But it does take some real thought when you're doing things. When you have big experiments like, the LHC experiments where they're testing hundreds of different channels all the time, in that case, it's not reasonable to sort of try to quantify the look elsewhere effect across every single thing that's happening. But this is why people are just generally wary of results that come out, right? Because if you have hundreds of different analyses happening, the chances of getting a 3 sigma result from one of them is actually really high, right? Which is why people don't get too excited for the first time you see it. You wait for someone to update the analysis with more data and see if it continues getting bigger. Because typically if there's a systematic effect, which is either there is actually a real physics effect, or maybe there's just an unmodeled systematic. In either case, as you collect more data, the significance should keep going up. Whereas if it was just a statistical fluke, then the chances of going down are just as high as going up. So ideally, in any situation like that, you would wait for sort of another tranche of data to come out before you really are convinced that something is really happening. But this just is just saying you should be very careful about interpreting what you're seeing, because a lot of discrepant things can happen by chance if you have a fleet of students analyzing many, many different things. Okay, now point estimation. So point estimation is basically saying, I have a model that's not fully specified, right? It has free parameters. I would like to know what those parameters are. There is something called the maximum likelihood principle. It's sort of an intuitive thing, not necessarily something that has, I think it's probably fair to say that it's not exactly like a rigorously defined thing. But the idea is that if you can make a likelihood, right? So you're saying, what is the probability of having observed this data given a model? And then you say, this model has different parameters, right? And if you move the parameters around and recalculate your likelihood over and over again, the set of parameters that make that likelihood as big as possible in some ways is more right than any of the other models that you have, right? Because it has the data had the highest probability of being drawn from that model, and therefore this is probably a better model for that data than the other versions of the models you have. So this principle is sort of at play at pretty much all fitting you do. The other thing that's nice is that if you have a parameter estimator, so that's what this would be called. This is something that lets you estimate parameters. Parameters of this form can be shown to at least asymptotically be unbiased, efficient, normal, and invariant under transformations. So what does that mean? Unbiased means if the estimator of your parameter minus the true value of the parameter becomes arbitrarily small as you collect more data, right? So that's about the bias term. The expectation value between the difference between those two things should become arbitrarily small as you collect more data. Efficient means the variance of your estimator is the smallest of any other option, right? So any other estimator would give you a larger variance than this one, right? So maximum likelihood estimators typically give you the lowest variance of any other option. They tend towards normal, which in some ways is saying they tend towards being chi-squared distributed as you collect a lot of data. All of these tend to be that case. And invariant transformation means if you change a variable in your likelihood, it doesn't actually change your result at all, which is very nice to have happen. So all likelihoods are of this form. You have bins, like n bins, and each of those bins has some probability distribution, right, of seeing what you observed in that bin given a model characterized by some parameters that we call, this vector theta, right? So that's just the list of all the parameters that you need to fully specify your model. Because you can think of each bin as basically being independent, the probability of seeing the set of data that you actually saw, for all the bins, is the product of the individual likelihoods of every bin. And then when we want to maximize it, basically what you want to do is you want to take the derivative of the likelihood with respect to each one of your parameters and set that equal to 0. Like I said before, products are hard to deal with, and taking the derivatives like that of a product is messy. It's much, much nicer to be able to take the derivative of sum instead. The natural log is monotonic, and so it shouldn't change the location of the maximum. So we can take a natural log of our likelihood, and the place that the parameters that maximize the likelihood should also maximize the log likelihood. The other thing is that most optimization algorithms that we have actually find minima, not maxima. So we want it to be negative instead of positive. So we put a negative in front of the whole thing. And then finally, there are proofs to show that if you multiply the whole thing by 2, this converges towards a chi-squared distribution in the limit of infinite statistics. So all that to say is that we like to take the -2 log likelihood. The very last bit is that we actually use a likelihood ratio. This thing below is a little bit weird, but it's basically the likelihood of getting the data if your expectations were the data, right? Which in the context of a Gaussian likelihood doesn't make a lot of sense, but in the context of Poisson likelihoods, it actually gives you a nice normalization factor. And this actually is important if you want to use like other types of likelihoods in something like a chi-squared test. You need to sort of do that to make everything work. So this thing here is asymptotically chi-squared distributed, which we make use of quite a lot to at least get rough results. Okay, so now this is the Gaussian likelihood. I showed you before that this gives you literally the chi-squared. The role that this is playing, right, the L naught, is if you plug in for mu, you plug an x into it, then you get 0 in this term, right? So the likelihood of x given x is equal to n over root 2 pi sigma I squared right? So that's 0. So this is just equal to this constant. So when you take the negative log, right? When you take the negative log of this quotient here, essentially what this does is it removes the constant that you get from the normalization factor, right? So that extra term there just removes that constant for you. Once you have that, you can use it to do a linear fit. So let's just say this is something I'd like you to do after you're done here. So it is, imagine you have 4 data points, right? So our y values are 2.3, 2.5, 4.25, and 4.75. Our x values are just 0, 1, 2, and 3, and our sigma is 0.5. We believe that the data points were derived from a linear model. We want to know what the best slope and intercept is. So I would like you to do this by hand. Like you can of course plug this. You could type this into root and like fit it. But I would like you to do it by hand because it turns out it's actually very easy, and you should know how to do that. So to get started, just remember that chi-squared equals the sum over your bins of y minus mu I over sigma I squared. Our model says that mu, as a function of your slope and intercept, should be m x sub I plus b. So that means that your chi-squared is going to be equal to y sub I minus m sub I minus b over sigma I all squared. And then you'll want to set these equal to 0. And that'll give you a system of linear equations that you can really easily solve just through some basic matrix math. So you should be able to estimate what those are. I just wanted to take a quick, just quickly say that the result you're going to get, the form of those linear equations are extremely close to what you would get from ordinary least squares. And so if you haven't actually seen how ordinary least squares works, you should. So the idea is, let's say you collect n data points, right? And you have a model that you think distributed them. So we have a series of equations. Right? This is a series of n equations, but we only have 2 unknowns. So this is an overspecified linear system. So the way you normally write this is you have your vector of observations is equal to this. That's not anything you can do anything with, But if you multiply by the transpose of this matrix, or this matrix, you get something like this, which gives you something like that, right? And that winds up being very, very close to what you get from optimizing your chi-squared, right? So again, this can be solved just by inverting that matrix. And this is something that people should have, sort of just something they know how to do, that you don't always have to just like have root do it for you. There are times when this is something you can actually do on a back of an envelope and just check. Okay, now Poisson likelihoods. So the Poisson PDF is this, right? So this is the probability of observing n counts if your expectation is new. So we can make our likelihood, which is the product of that for each bin, and then we make that into a -2 log likelihood like this. And it's actually the likelihood ratio. So the form of this involves sort of setting all of your news to n for your L naught in the ratio. So if you ever have any doubt whether or not your bins are large enough that you can use the Gaussian approximation, you should use this. The other thing is that this method correctly handles bins with 0 observed counts, whereas chi-squared doesn't necessarily, right? So the statistical uncertainty on a bin in the Gaussian method when you go to 0 counts doesn't make any sense, but the uncertainty here is perfectly well defined. So you should always use this if there's any possibility of 0 observed counts in a bin. Now, what we did before was linear fitting. That's just basically inverting a matrix, and it's something you can do by hand. If you have a system of equations, the system of equations you get from the Poisson likelihood is almost always nonlinear. There are many optimizers that exist to minimize the objective function. Min-UE is what's sort of built into root and is very common in high-energy physics. It has 2 different optimizers in it. It has migrad, which basically computes the Hessian matrix, the matrix of second derivatives, to build parabolas. So it's basically doing a second order approximation of the likelihood around a point, and then basically finding the minimum point of the parabola and jumping to that. And then you recalculate your Hessian and do it again until the minimum of the parabola doesn't move anymore. It's very, very fast if the function is well behaved, and it has an internal estimate of the distance to the minimum, basically like how far does the bottom of the parabola have to move to get an idea of whether or not you've converged. It also has simplex, which uses geometrical objects to find the minimum. It's a gradient-free approach. It doesn't use gradients or Hessian matrices. So if you have any doubt, if your function is not necessarily numerically well behaved, where you can't take numerical derivatives easily, that might help you, but it's really slow and doesn't really know when it's converged, right? So you just run it for a while and see what happens. There's no surefire way to minimize a function with multiple minima, and it very often happens, especially when you're in low statistics, that there are many minima. You should always do a parameter scan whenever you're trying to figure out if your fit makes sense, right? So if you basically plot your different parameters and just evaluate your objective function in a grid and look at it and say, does it look lumpy? If it looks lumpy, there's a good chance your minimizer is getting stuck in one of the lumps and not in the place that you actually want it to be. And so that's something that you want to be able to check. So if you want to do an analysis with precision, you have to make sure that you can robustly find the true minimum, even in the presence of reasonable fluctuations. So almost always you should do pseudo experiments where you fluctuate your predictions according to your systematic and statistical uncertainties and refit over and over again to make sure that you can reliably get the right answer. And you have to make your fitter robust enough that that happens. Otherwise, you just get wrong answers. Okay, now systematic uncertainties. Systematic uncertainties are when the prediction you're trying to fit to data depends on parameters that are imperfectly known, right? So there are many, many things. John talked about a whole bunch of them already, but there are tons of places where we have maybe made idealized assumptions, and we need to account for that. You should never trust an analysis that has not thought through its systematic uncertainties. If you ever see this person give a talk and they say, we've just done statistical uncertainties, but if this is interesting, you should just not listen and walk away, because nothing they've said means anything until they've done an analysis with systematic uncertainties. You just have no idea what the answer is until you've done that. And it's critical to think about that early. It's not an afterthought, right? That's the first thing you should be thinking about, are what are the systematic uncertainties that might be affecting a measurement that you want to do. To evaluate them in general, we need to figure out, if you identify a source of mismodeling, you need to determine how that prediction changes as you change that parameter, right? So the amount you change the parameter could be guided by an auxiliary measurement, but often it's just an informed guess, which means that systematic uncertainties are inherently a little bit more Bayesian than like just inherently, because it's really about like, what do you believe the range that parameter could really realistically have, which may be guided by lots of things, but it's a pretty subjective thing that you have to work with. So this here shows you basically the muon neutrino charge current sample if you change the shower energy scale, right? So converting from the sum of energy of observed energies in a shower to what we think the true energy is for that shower. If you change that by plus and minus 1 sigma, you slide all your events one way or another, which changes your result by up to 4%. Now, if you want to incorporate these, you have to think about what the combined statistical and systematic likelihood is. So imagine you have a parameter beta, which controls the size of a particular systematic uncertainty. So we want to construct things so that when beta equals 1, you're at the plus 1 sigma error band. And when beta equals minus 1, you're at the minus 1 sigma error band. And then when beta is anything between, it sort of interpolates between them. So if we construct this correctly, we can imagine that parameter beta being Gaussian distributed with a unit Gaussian. A joint likelihood is just a product of different likelihoods. So we have the product of the likelihood of each bin, right, is the statistical likelihood. If you then multiply by the likelihood of the systematic parameter, you basically get these extra terms that we call penalty terms. So you get something that looks like this. This is the normal Poisson likelihood, and then these are penalty terms, which are penalizing each one of our systematic effects. So the idea is that your likelihood gets bigger if you move away from your nominal systematic, right? When your systematic parameter is 0, that's your default nominal prediction, and as you pull away, you're sort of morphing towards your error bands. And there's a short article on the archive which was sort of like my Bible going through my PhD, so it's really helpful for thinking about these things. To incorporate these, you can model how things change by basically taking your default nominal prediction as your new one, and then the product of all of these systematic scale factors tells you how to morph according to all of your different systematics. So this is like a approximation of everything that everything you could do to make it change. And then you need to figure out how your alphas are a function of your betas, and you can use this Lagrange interpolation, right, to basically figure out what your alpha is as a function of beta, right? So as beta moves around, it tells you how to interpolate between these different error bands, right? This pull method lets us include systematic uncertainties that are fully correlated. So it's not just saying that like we have an extra certain percentage of uncertainty in every bin. This is saying that it actually has to move with this shape, right? We have a systematic uncertainty that we think has some sort of shape, and we actually want to try to find deviations in our data that match sort of the shape of that particular uncertainty. So this is very commonly used. You can also extend this formula by just doing a linear extrapolation for greater than 1 and less than -1, which is an exercise that you should probably just try doing. You can also do higher order Lagrange interpolations if you have sort of error bands that are 2 sigma error bands and 3 sigma error bands. In practice, you shouldn't really need those because if you've gone much further than 1 sigma, you've probably pulled hard enough that your models are not working well. The other way you can handle this is through a multivariate Gaussian likelihood. So this is basically saying that all of your bins are correlated with each other. You're basically drawing your bins from a multivariate Gaussian. So each bin is Gaussian distributed, but they have correlations between them. And that's coming from the systematic. So you have an uncorrelated part, which is your statistical uncertainty, and a correlated part, which is your systematic uncertainty. So the pull method is very useful, but it has some issues, which is that every systematic is a new parameter that you have to fit for. And min-UE tends to struggle the more parameters you put into it. And you can only include fully correlated uncertainties. So if you derive it like the way I showed with error bands, then it works. But let's say you have some simulation-based uncertainty where you randomly change many parameters within their uncertainty. That naturally comes out as a covariance matrix, not as a single band, right? You can't, another way of saying is that you can't reduce that to a single degree of freedom, right? You have to need many parameters to control that morphing. So you could naturally handle it a different way. The multivariate Gaussian replaces pulls with a covariance matrix using this sort of chi-squared equivalent. Your covariance matrix, you can calculate a covariance matrix per systematic, and then you add up all the covariance matrices to get your final covariance matrix. That's just equivalent to adding your uncertainties in quadrature in a correlated way. But since the uncertainties aren't optimized at fit time, you can't judge post-fit agreement by eye. So that's like one of the downfalls. And this is from a far detector, near detector joint covariance matrix from the 2018 Minos plus Darrell search that used this technique. There's also something where you could try to get the best of both worlds, which is try to make a hybrid Poisson-Gaussian likelihood. This is something that my group has been working on a while to do. The idea is that this is the Poisson part, but in each bin you have a scale factor, which is your systematic scale factor, and the systematic scale factors are constrained by a multivariate Gaussian. So it's not the bins themselves you're constraining anymore, it's the scale factor. Now that gives you a ton of parameters. You basically had a parameter per bin and per component you add together in your bin. So that may seem like you've really lost. But one nice thing is that you can actually analytically write down what the gradient as a function of all of those new poles are and what the Hessian matrix as a function of all those poles are. And so once you have that, you can actually use Newton's method to quickly optimize all the systematic poles for a given set of physics parameters. So you basically fix your physics parameters, solve Newton's method iteratively, and then use min-UE to get you to your to optimize your physics parameters. And this was used in the 2022 Nova sterile analysis. Okay, just do a little bit of interval estimation. So once you know what your best fit point is, that alone doesn't tell you really anything, right? An answer without uncertainties, again, doesn't mean anything. So you need to figure out some estimate of the uncertainty of the result. The frequentist idea is that if you have a confidence interval of alpha%, that means that if we repeated the experiment many times, alpha% of the confidence intervals would include the true parameter, right? So we have our true value over here. We've drawn, for each one of these fake experiments, we've drawn a interval that we've predicted, and the number of them that don't touch the true value is 1 minus alpha fraction, right? So 68.3% confidence level bands correspond to our conception of error bands. The classical way of doing this is the Niemann construction. The idea is that you construct something called a confidence belt. The idea is for every value of your parameters that you could have gotten, for the true parameter, you say for a given value of your true parameter, you run fake experiments and figure out what values you could have gotten, and you basically make an interval which contains alpha % of the pseudo experiments for that true value. And then you stitch that together for all of your parameters. Once you have that confidence belt, if you observe a particular value in your data, you basically draw your line down here, and you look at all of the segments of the confidence belt that intersect it, and then propagate it this way. And this is your best fit, and that is your confidence interval around that belt. So this is sort of from the PDG statistics review, which is another thing I recommend you taking a look at. That's the sort of the classical way of doing it. It turns out there are actually lots of ways to draw confidence intervals, and we'll talk about that a little bit more. But I think we're out of time, so I'll finish that up tomorrow.
Thanks, Adam. So any questions?
Hi, in slide 7, you mentioned p-value should be equally distributed if the null hypothesis is true. Could you elaborate that?
Which slide was it?
7.
So, okay, what was the question?
You mentioned the p-value should be equally distributed.
Yes, right. So if you redo your, so in some ways what you do is you make your pseudo experiments to figure out the distribution of your test statistic, right? If you then take any of those pseudo experiments and use them as your data and compute your p-value, right? And then plot that p-value in another plot, and then do that for every one of your pseudo experiments that made up your distribution, the distribution of p-values you could have gotten is now a uniform between 0 and 1. So the idea is that if the null hypothesis is in fact true, you should expect to get any number between 0 and 1 with equal chance.
Okay.
Hi.
Yeah.
You just showed the two minimizers, I minute and that migrant. So can you just explain it a little more? What is the issue with this I minute minimizer?
So Minui, people often say if you don't know anything about your problem other than your likelihood, Minui is the best option, right? It's a general purpose fitter. If you go online and look for optimizers, you will find other things that are used in industry. But in almost every case, all those options require some extra knowledge about your function that you're minimizing that you may not have, right? So if you don't know anything, the best thing to do is use Minui. Migrad is the default minimizer that Minui uses. So Minui is a package, and within that package, it has different minimizers it can use, right? And Migrad is the default one, and it usually works pretty well. The main reason why it might not work well is that the Hessian matrix is computed numerically, right? So you basically do finite differences, right, to compute your gradient. And then you do finite differences of that to compute your second derivatives to make up your Hessian matrix. If you have numerical imprecision in your function, the noise in the derivatives might be large enough that Migrad goes crazy, right? So sometimes when you do a fit, you'll be watching and an error message will come up which will say that the Hessian matrix is not positive definite, moving to the nearest I forget what it says, but what it does is it basically the Hessian matrix becomes not positive definite, which means there's no parabolic solution that it can actually build. And so it does a thing where it finds some subspace, which is good, and takes a big step. But sometimes that step just sort of zooms off to infinity, and then it spirals out of control, and the minimization fails. And that's sort of there's these common failure methods like that, which mostly come from the fact that computers have finite precision. And you're computing, if your objective function is complicated and you're doing many, many additions and multiplications, it may actually have less precision than the stated machine precision. right? So there are subtleties you can do where you can tell root what the precision actually is. Like root does some checks to figure out what the precision should be, and it uses that when it's calculating its derivatives, it uses that to figure those out. But it might be wrong, right? So like, for instance, this hybrid method we use, we do a Newton's method iteration in between every Minuit iteration. And we stop the Newton's method when it converges within e to the minus 5. But that's bigger than what root thinks machine precision is. So sometimes Minuit gets confused because things are choppier than it expects. But that's something we can just tell it. We can tell it that Mercian precision is e to the minus 5 instead of what it thinks it is, and then it smooths things out more, realizing that the derivatives are not as reliable as it thinks it is. So it's stuff like that. There's the Minuit manual. If you look up Frederick James's Minuit manual, he's the main author of it. He actually has a whole book about this entire problem, and it's incredibly informative. So I actually would recommend you find his book. It's really helpful for understanding all of these issues, because it is like the thing grad students spend like a year on, is just like trying to get repeated, robust results out of a fitter all the time. So it's worth spending some time on.
It's very, very slow migrate.
What's that?
This migrate is very, very slow.
It is very slow. There are lots of tricks you can do. There are things where you can do like low precision first approximations followed by a higher precision refinement, which can allow you to do it faster. But the reality is that it's probably going to be slow, and you're going to need to have access to a computing grid. Once you've made sure, the idea is that to make it robust, sometimes you have to sample at multiple starting points, and you have to do things where you start with some parameters fixed, and you gradually expand your search space, things like that. And all of those things take extra time, and there may not be a way to improve things beyond that. So if you find that your problem is tricky enough that you have to really help Minuit, you might need to just get access to a computing grid to do what you want to do.
So let's say this Minuit minimizer is failing for some points.
Yeah.
So what we can do to get the good recovery of the parameter, let's say.
Yeah, so this is something we should probably talk about this after. That's a huge topic. There are lots and lots of things you can try, but I would say the very first thing I would do is make one-dimensional scans where you scan a parameter and you plot your objective function versus that parameter, and just look at, that's called the profile likelihood. So you're minimizing over all the other parameters, and then you're just scanning over one parameter. And if that is really jagged, something is wrong, right? That's sort of like the first hint that something in the minimization is going wrong in a way that's causing real problems. And if you do that for all of your parameters, you can usually isolate which parameter is causing the problem and go through and figure out why it is. Sometimes it's really just like a way you coded up that parameter. Like in Nova, we had an issue where when we were fitting a phase, there was a problem, and it's because the code, right, phase is only defined from 0 to 2 pi, but 0 and 2 pi are the same thing. And Minuit doesn't really know how to minimize on a circle. As far as I can tell, no minimizers know how to do that. And so we did a thing where if you go past 2 pi or 0, it resets you, right? But it reset you by subtracting off 2 pi multiple times or adding 2 pi multiple times. And the numerical error of doing that built up to where you actually didn't get back to the equivalent point. And so if you had to do it a bunch, like if Minuit jumped you to like 1,000 pi and you had to cycle your way all the way back into the 0 to 2 pi range, you accumulated so much error that your answer had nothing to do with your original answer. And it completely messed up all of the derivative calculations. And so once we knew that, we just calculated it differently. We did it in one step instead of iteratively, and it worked fine. So oftentimes, if you can isolate what it is, if it's something like that, it might just be that the way you coded up the behavior of a parameter has an unacceptable amount of round off. Because remember, computers are finite precision. It's not like you write down all your formulas using like real math, but that's not what the computer's doing. And there's lots of complicated things you can write down which have like very, very bad round off errors. And so oftentimes you have to look into it and think, is there a way I can rewrite this that's better for a computer? It might be a messier way of writing it, but it's better for the computer to get a more robust result.
Thank you.
Hmm? Yes. Exactly. Yeah, so in Minos and Nova, we've handled this by multiple seeding. So you have to know the structure of your space, right? So when you go from one mass orbiting to the other, there's a hard cut. And when you go from below maximal mixing to above maximal mixing, there's a hard cut. And you have to know the places where there's degeneracies. And the most likely, the thing what you have to do is you have to just start your fit in each region, do your fit separately, and then pick the best one of all of them to do it. And that requires understanding your space. So like I do a lot of sterile searches, and in sterile searches, all of these issues that happen with free flavor are just multiplied by 10, right? Because it's like you have many different ways of having maximal mixing. You have solutions where your standard like theta 1,3 and theta 2,3 and theta 2,4 can swap places and like change their roles, right? And all of these things which you can't have like continuous derivatives through those things. Minui will never work. So you actually have to understand, sometimes getting the right answer requires understanding the parameter space really well and understanding the places where like you can have your likelihood will get these long deep valleys that the minimizer will never be able to figure out how to get into, right? And sometimes that means like multiple seeding or like applying some sort of transformation to your parameter space, right? To account for the fact that you get these regions where you sort of flow in weirdly correlated ways. But those are tricks that you have to, there's not like a rule book on how to do it. There's lots of things you can try, but sometimes it's like they're very clever solutions you have to come up with to make it work. Yes. Yeah. Yeah, you have to debug what, like that's what I'm saying. When you make surfaces, you have to plot the whole thing to find, you can't just like believe Minui that it did the right thing. You have to check because it very often, like exactly what you're saying, there are issues with small numbers or issues with features in the parameter space which cause problems that you could easily just turn the crank, get an answer, and it's just entirely wrong. And you would never know unless you look at the details. And like this is something that we have to fight with our students. When students first join NOVA, we have to fight with them to get them to do this because they don't believe us until they look at these profiles and realize that yes, in fact, it looks horrible. It doesn't make any sense. And that like something special has to be done. So don't believe it. It works great. I'm not trying to bash it. It's just that like, it's a black box that you need to really investigate what it's doing to find out if it's doing the right thing.
Okay, I think, Adam, you can correct me to his question about this Minui failing, if I am wrong. So I think normally Minui, when you are some parameter you are trying to estimate at it hitting the physical boundary, like cos sin theta per 0 to 1,
yeah.
Most often it hitting the 1 because it cannot go beyond 1. That's when you have to come back to this Neumann construction. You said what is the way out. So there is a Neumann construction, I think, but that construction is very delicate with a likelihood ratio ordering and so on.
Yeah.
I think you have not gone through the many things coverage test. So this is the way also to go actually. You have, and that's very, maybe sometime we can discuss with you. Yeah, when you're trying to measure some parameter and it is a physical boundary, it cannot go beyond than that.
Yeah, so I have slides on that. If I start to explain, it's going to take too long. So I'll finish that tomorrow. But yeah, there are techniques for handling. Yes. And there are other options, but that's what NOVA uses. Yeah, and it's common. It's explicitly designed to handle that problem. So for instance, the Neumann construction, you can wind up with empty intervals, right? Where your answer is actually beyond the best fit answer is actually beyond what the model can give you. And so you get a confidence interval that's 0, an empty interval. And the thing that's particularly upsetting about that, right, is that if you have a 90% confidence interval, you should say that only 10% of the time should you have an interval that doesn't have the true value in it. But of course, if you have an empty interval, you know for 100% certain that you are in the 10% where it's wrong, right? Like you know for a fact that you have the wrong answer. And there's something a little bit unsettling about a method that can do that. So there's ways of handling it that I'll talk about a little bit tomorrow.
Okay, let's thanks Adam again. And